Dear students, we are discussing first order differential equations. Now we will see what are the applications of first order differential equations. We know that the first order differential equation has a general solution which contains one arbitrary constant. Now this constant is called a parameter. When this parameter is assigned various values, we get one parameter family of curves. Each of these curves is a particular solution or integral curve of the given differential equation. Now, some general remarks on applications. Consider the equation, first order equation dy by dx plus p of x into y is equal to q of x. We take it as equation 1. Usually here the independent variable x will be time. So x equal to time, and correspondingly the dependent variable y is a function of x, it will be again a function y of t. Okay, it may be displacement, current, or some other physical variable. So it can be regarded as an input-output process. So in engineering mathematics, usually our q of t is the input and y of t is the output or response to the input. So we can have a diagrammatic representation of the first order differential equation. Okay, q of t is the input and y of t is the corresponding output. Usually q of t is the force in engineering mathematics, mechanical vibration, etc. And y of t is corresponding displacement. So the general solution of a first order differential equation is of the form y of t into integrating factor equal to integral of q of t into integrating factor dt plus c. Okay, so this integral is evaluated with respect to t. Okay, so in application it represents the total output to the system is response to it is a sum of the response to the inputs and the response to the initial data. Okay, now we will see some applications of the first order differential equation in geometry. As we know, the general solution of a first order differential equation represents a one parameter family of curves. So to find the orthogonal trajectories of such curves. So what do you mean by trajectory? What is an isogonal trajectory? What is an orthogonal trajectory? Now, an isogonal trajectory means a family of curves which intersects a given family of curves at constant angles. Okay. In particular, this angle of intersection is 90 degree. Such family is called orthogonal trajectory. More precisely, a family of curves which intersects a given family of curves at right angles, and conversely is called the orthogonal trajectories of the given family of curves. So, for example, we know the meridians on Earth's surface are orthogonal trajectories of the parallels. All of you know that. Similarly, the family of straight lines through the origin is the orthogonal trajectory of the family of concentric circles centered at the origin. You can see it from the figure. Okay, here we have two families of curves. First family is the family of concentric circles centered at the origin, and second family is the family of straight lines passing through the origin. From figure it is very clear that each of the two families are intersecting at right angles, hence they will form an orthogonal net. Okay, now how to find the orthogonal trajectory? Suppose we are given a family of curves whose equation is given by capital F for f1 of x, y, c1 equal to 0, where C1 is the parameter or arbitrary constant. Now it is a parameter. So it is a one parameter family of curves. First of all, we have to find the differential equation of the given family. For that, differentiating equation 1, we will get an equation involving dy by dx. Okay, so eliminating the arbitrary constant C1 from this equation and the given equation 1, we get a differential equation of the form dy by dx equal to some small f of xy. You take it as equation 2. Next, the orthogonal trajectory and the given differential equation given family has a connection. What is the relation? The differential equation of the orthogonal trajectory and the given family are they have slopes, the product of slope equal to -1 since they are perpendicular, they are orthogonal. Okay, hence if you write the slope of the given family, it is dy by dx equal to small f of xy. So slope of the required family, the orthogonal trajectory, will be negative reciprocal of the given family, that of the given family. So its slope will be dy by dx equal to -1 by f of xy. On simplification, it is equal to minus dx by dy is f of xy. You call it as equation 3. Now solving equation 3, we will get the required equation of the orthogonal trajectory in the form, say, f2 of x, y, c2 equal to 0, where c2 is an arbitrary constant. Now geometrically it is a one parameter family. So equation 4 represents the orthogonal trajectory of the equation of the orthogonal trajectory of the given family. Okay. Now from figure we have two families, f1 and f2. They are represented. They will intersect at a point. So each member of the first family intersect the second family at right angles. So at the point of intersection, say we have T1 and T2 are the respective tangents having slopes m1 and m2. Product of slope is equal to -1. So mt is equal to -1 by m1. That is why we are replacing dy by dx by -1 by dy by dx to get the differential equation of the orthogonal trajectory. Okay. Now, as an illustration, first we find the orthogonal trajectory of the family of parabolas y is equal to ax square. For that, we take y equal to ax square as equation 1. Okay, equation 1. Now, differentiating equation 1 with respect to x, we will get dy by dy is equal to 2ax. You call it as equation 2. Now, by eliminating the arbitrary constant small a from equation 1 and equation 2, we will get the differential equation of the given family. Okay, it is obtained as dy by dy is equal to 2y by x. Since a is equal to y by x square from equation 1, you substitute the value of a in equation 2, we will get the differential equation of the given family as dy by dy is equal to 2y by x. Now, differential equation of the orthogonal trajectory will be obtained by replacing dy by dx in equation 2 by minus dx by dy. Okay, that is, we are getting dy by dx equal to minus x by 2y. Okay. Now, this is the differential equation of the orthogonal trajectory, but we need the equation to the orthogonal trajectory. How do we get it? You just solve equation 4. Equation 4, we are getting x square by 2 plus y square equal to c square. What is it? It represents a family of ellipse. Okay, family of ellipse. Now we can see its geometry. Okay, so first family is y is equal to x square. Ax square is a family of parabolas. When a is positive, it is upward parabola. When a is negative, it is downward parabola. When a is equal to 0, it represents the x-axis. Okay, and x square by 2 plus y square equal to c represents family of ellipse. Okay, Now we see another example. To find the orthogonal trajectory of the family of circles h square plus y square equal to a square. We have seen in the introduction itself that the orthogonal trajectory of the family of family of circles, concentric circles centered at the origin is the family of straight lines, but we have to verify it. Okay. For that, differentiating equation 1 with respect to x, we will get 2x plus 2y dy by dx equal to 0. From this, dy by dx equal to minus x by y. Here the arbitrary constant a is eliminated. So equation 2 can be taken as the differential equation of the given family. Okay. Next, what we do? We have to find the differential equation of the orthogonal trajectory. How do we get it? Just replacing dy by dx in this equation by minus dx by dy, which gives dy by dx equal to y by x in turn. Okay. So, which is variable separable? This is the differential equation of the orthogonal trajectory. So, solving this equation, we will get the required equation of the orthogonal trajectory as y is equal to cx. Y is equal to cx, where c is an arbitrary constant. In general, it represents family of straight lines passing through the origin. Hence, the figure. Okay. I hope that you followed this concept and figure. Okay. You practice similar problems. I will giving some exercise for you. Find the equation to the orthogonal trajectory of the following curves. Cos x sinh y equal to c. Next, h square minus y square equal to a square. It's a family of hyperbolas. Now hy is equal to c square, which represents family of rectangular hyperbola. So it is a geometry of the Boyle's law. Okay. Fourth one is h square plus 5 minus c the whole square equal to c square. It's a family of circles. Fifth one, h raised to 2 by 3 plus 5 raised to 2 by 3 equal to a raised to 2 by 3, which represents a family of asteroids. Okay. A is the arbitrary constant. Okay. Thank you for watching this video.